Hello everyone, my name is Butlako and welcome to one of the first videos we're going to be having in our calculus series. We'll be starting off with the deriving using the first principle. Now, when you think about getting a gradient of anything, the first thing you think of oftentimes is using your gradient formula that you learned in analytical geometry, this formula right here. If we needed the gradient of a straight line, right, a linear function, let's call it g, and we had 2 points on the linear function. Ignore the parabola for now. We had point A and we had point B on the linear function. If we wanted to find the gradient, we could simply take the coordinate values of A and B and plug them into our normal gradient equation. But when it comes to curves, we are confronted with a very big problem. The problem when it comes to curves is that the gradient is always changing depending on which point you are on the curve. So because of that, we can calculate the average gradient of a curve, but it's very hard to calculate the gradient of a particular point on a curve. So ask yourself, how did we even do it in the olden days? How did we find the instantaneous rate of change or the gradient at a specific point? Well, today I'm going to teach you how the logic behind the first principle works. Say you have this line g at x, cutting a curve twice. One could argue that from A to B, say you have this linear function g at x, and it intercepts the graph twice, right? So let's say it intercepts the graph first at A, right, with a value of x, and then it intersects the graph at B with the value of x plus h being the distance between the A x coordinate and the B x coordinate. We could argue that the gradient you get here would be the average gradient of the curve. But the average gradient of the curve is not accurate enough. So I want to ask you a very simple question. What would happen if we made h smaller? What would happen if we made h so small that h was a near zero value? That means what happens if you make h so close to zero that it almost is zero? Okay, you're going to ask me, why can't we make it zero? I'm going to answer your question on why we can't make it zero in a bit. So you see the linear function here, g at x. Let's assume this linear function shares the same gradient as h at x. Now let's move h at x closer, and let's move it closer. We're moving it proportionally, which means all these different variations of this g at x function have the same gradient, but of course they're going to be formulated differently. What happened if you moved it so close that it only cuts the curve once? If it only cut the curve once, we can agree that h would be 0. But we don't want it when it cuts the curve once. We want it just as it's about to cut the curve once, and I'll explain that. But let's say we do make this secant line, secant meaning it is a linear function that cuts a curve at 2 points. We make it a tangent line, meaning that it is a linear function that cuts a curve at 1 point. Could we all agree that this point, C, has the gradient of g at x? Because g at x has the same gradient as all these other variations of that function. But now we've brought it to the point C. But now we run into another problem. What happens if you want the gradient of this point? You're going to have to draw a function from A to B and hope it lands there. What if it doesn't land exactly there? And if we had to draw every single time we wanted to get the gradient at a particular point on a curve, it would take forever. So the olden ancient mathematicians had to derive a simple way of doing things. And you're going to say to me, okay, but like, what is that simple way of doing things? Well, it's simple. Oh, that's ironic. So, one thing we can agree, the coordinates of A would be what? It would be first the x coordinate, which is x literally, and then the y coordinate, which is f at x, right? And then of B, we'd have what? X plus h, and we'd have f of x plus h. This would be the coordinates of this graph right here. Now you might say to me, but like, what if I said f at x is first and the other one is next? Like, what if you chose to make A's coordinates 2 and B's coordinates 1? Well, my argument is you'd still end up getting the same thing, because what would happen is this would be positive, this would be negative, right? This would be negative, this would be positive. So the x's would cancel out and you'd have a negative h. Then your negative h up here, you could kind of divide, right? Since you're dividing by a negative number, right, you can take out a common factor of -1. Then whatever at the top would switch value. So you'd still end up with this equation. But all this equation is simply saying is y of A, right? No, y of B minus y of A, right, over the x of B minus the x of A. And then you see this x cancels out with this x, and then you get h. If you did swap them around, you can do it for yourself quickly. You'll see that you can still get this formula, because you'll have a negative h, and then of course you don't want a negative denominator. You could kind of cancel that out by dividing the negative sign into the numerator, but that will switch the signs, and then you'll see if you switch the signs, you end up with this bad boy here. But now there's a problem, and our big problem is the fact that h cannot be 0. Because if h is 0, that means that this function here is useless, right? Because it means this function is useless, because you cannot divide any term by 0. So since you can't divide any term by 0, you want h to be very close to 0, but not 0. And that's when this notation comes in. The limit as h approaches 0, basically meaning as h gets very, 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 very close to 0. Oops. As you guys can see, I'm working on a budget. As h gets very close to 0, that allows us to use this formula and have this formula not be undefined. Because our problem is we couldn't use it here because it was undefined. So we can use it here because it's not undefined, because h is not 0. H is just very close to 0, very close to 0. And that is why we're using the limit of h in this case, and not just using this formula the way we're seeing it. Okay, so we're getting into our first example. The first thing I always advise people to do, I almost said students, but I'm also a student. I always advise people to do is to first work out f at x plus h. Don't work it out while you're doing whatever you're doing. Work it out before. So f at x plus h equals to this function. But wherever you see x, you're supposed to replace it with f at, no, not f at x. You're supposed to replace it with x plus h. Remember, if this was 1, you would get in here and you'd say 4 brackets 1, 2. Treat this the same. Don't algebra it. Substitute it into the equation. So you're going to have 4, right? X plus 1 minus 3, x plus h. I said x plus 1 by mistake. My apologies. It's going to give you 4x squared plus 2xh plus h squared minus 3x plus h, which is going to give you 4x squared plus 8xh plus 4 squared 3x plus h. Perfection. And then once you get to this part, you can see, is there anything that you can cancel out for anything else? No, there is not. Okay, guys, so I kind of skipped over a few things. because I wasn't recording by mistake. So quickly to fix my mistake from the last video is here, or the last part of the video. Here, it is negative 3, right? When you multiply it into the bracket, it's negative 3x, negative 3h, right? Then you multiply the 4 into the bracket, you get 4x squared plus 8xh plus 4h squared, right? This is equal to our f at x plus h, right? We did it separately, which is always a good thing. I always advise it. Then you come here and you write the fact that the first derivative equals to the limit as h approaches 0, right? And the formula. You need to use the limit again. Why do I need to use the limit? You need to use the limit because h cannot be 0 in this state, because this is breaking the rules of math. So we go ahead and we substitute everything. The limit as h approaches 0, again, because h is still at the bottom. And then after that, we have 4x squared. We substitute everything in, right? This is the f at x plus h. And then minus, notice how I've put it in brackets, minus the f at x, which is the function we were given in the beginning, this function right here. So minus that function over h, right? So the number one rule about this method is whatever's in this bracket must cancel out. So look how here we have 4h squared, and here we have a 4h squared. But since this is negative in front of the bracket, this 4h squared is going to be a negative 4h squared. So negative 4h squared plus 4h squared is 0. So they cancel each other out, just gwa, gwa. Then after that, we get to negative 3x. This negative 3x, if you multiply the negative into the bracket, it will turn this negative 3x into a positive 3x. Positive 3x plus negative 3x is 0. We cancel that out. We cancel this out. This leaves us with these 3 terms up here. What do you notice about these 3 terms? The 3 terms are, they all possess an h. So we can factor out an h. We want to factor out an h. When you factor out the h, you must be happy. That's the second thing that we need. Because why? The moment you factor out an h, like I did here, you can cancel both the h's at the denominator and at the top. And that is good because now you don't have an h at the denominator. So you've been needing to say the limit as h approaches 0 because you did not want h to be 0, but you still wanted it to be close. So this can still be a good approximation, right? But now, since you've cancelled out h because you factored it out in the first place, you don't have h as a denominator. So since you don't have h as a denominator, you can actually just leave the limit as h approaches 0. You can actually leave this function, right? It's amazing. So now you can leave as the limit of h approaches 0 and just make h 0 because it's no longer in the denominator. You're no longer breaking the rules of math. And then you get 8x minus 3. And 8x minus 3, if we quickly just do the power rule up here, we know that 2 times 4 is 8. And then this 2 minus 1 is 1. So you're going to get 8x minus, right, negative 2x. Negative 2x, you have an exponent of 1 here. You multiply the 1 here. It's still going to give you 3x. And then if you subtract 1 exponent here, you're going to get x to the power of 0, which is 1. So it's the same as us just saying negative 3. And there you go. First principle calculus.